Right, there's a kind of book definition of actually what rise and fall time means. It's when a value, in the case of rise time, goes from 20% of a level up to 80% of a level. Or in the case of fall time, when it's at 80% of logic 1 down to when it's 20% of logic 1. So the time it takes to perform that transition is, in this case, the rise time, and in this case, the fall time. The faster the rise and fall time, the quicker you can make these transitions. And one of the things you have to be careful of, let's say that I'm not sure you want to be doing this in your design and build project, but you might, for example, have a shift register. Oops. Yeah, let's just say shift reg. And you're feeding in clock pulses to it, for example. There'll be a maximum clock frequency that it supports or whatever. If, for example, you're loading anything into latches, you're loading one value and then you're loading another value thereafter. There'll be a maximum speed at which you can do that, which is governed by, to some extent, the rise and fall time associated with that logic family. The rise and fall time, as I've mentioned, is typically family-based. So you might, for example, have CMOS technology, traditionally is regarded as a relatively slow technology. The rise and fall times are quite long in traditional CMOS. For those of you that remember things like TTL 7.4 series, I don't know if you've come across those, there are a whole set of families associated with that. L, which is low power, which is quite slow, quite long rise and fall times. There's LS, which is a little bit quicker, using kind of Schmidt triggers and things, I think. There's S, which uses a lot of current, but the rise and fall times are much, much shorter. So often you might see an S part where it's being used in a crystal circuit, straight after the crystal circuit, providing the clock source, high speed. You might see things like HC, which is high-speed CMOS. You might see HCT, high-speed CMOS with TTL-compatible input-outputs. And you might see something like F. So if you are buying like medium-scale integration components to be used as part of your design-build project, you'll find that for a particular part number, like a flip-flop or whatever you're going to do, an AND gate, there are different logic families open to you. And those different families have different rise and fall times associated with them. Okay, nothing else that's exciting on that one. So here's an example, and it's got a kind of an answer on the next slide, but we'll work it out from first principles, and I haven't looked to the next slide to know what the answer is. We'll just give it a go and see what we come up with. So, and this, something like this comes up occasionally in exam questions, where you'll be given a timing diagram, such as this, which actually shows you the relationship between various signals, and then you're asked to write a piece of assembly language in order to perform some action. Now, in this particular timing diagram, there are no numerical values associated with it. So we're only using it to work out the appropriate sequence of actions that we need to take. In the real world, it may be, for example, from the time that the address bus is stable to this write signal's gone low here, you would have to check in the data sheet, is there a minimum time here, a kind of setup time, that you need to be aware of, so that you don't perform this transition too quickly. But we're not going to worry about that. We're just going to try and get the sequence right. Okay, also we're being told that there are these useful instructions that we may wish to use. And I'll read what it says up there. In accordance with the diagram, produce a simple 8051 assembly language program to write the values, written twice, the values, 12 hex and OA hex to the registers 11 binary and 01 binary respectively. So we're assuming that the instruction latency, the time it takes to execute instructions, is sufficient that we don't need to worry about setup and hold times. So we've got to write a bit of code to achieve this. Okay. Now let's see what we've got. So we need to know which pins are being used for which of these signals. So we've got A0 and A1. Let's write these down. So we'll have P10 is A0, P11 is A1, the chip enable is P12, the write signal is P13, and the data is connected to part of port 3. So data is connected to P3 naught all the way to P3 6, and data 0 to 6. And we've been given these instructions. So this is effectively immediate dressing mode to load a value into an accumulator, instructions for setting and clearing individual bits, and this is saying moving from the accumulator to a particular port to write a value to that port, moving a whole byte. Okay, so now we have to look at the diagram. And we start from the left and work our way across, performing the appropriate transitions. Now I would have normally, it was me doing this, it's going to be a bit of a challenge. I can just about get it there. If I was working on something like this, I would chop this into phases and say, well, there's this kind of phase here where I'm kind of doing a setup to get those initial values. So that's going to be step 1. Then things are happening here, and they're going to be the next things that I'm going to do. Okay? Moving across, nothing changes until this point here. So the third things that I've got to deal with are associated with those transitions. Here, step 4. Here, there's something happening, so that's going to be the 5th thing I've got to worry about. Step 5. Lots of things happening here, that's going to be step 6. And then that's probably going to be it. So when I'm writing my code, I'm going to express it as a sequence of steps. Okay? So I could try and write it over here. Does that just... Chip name is the highest. Okay. Right, so first of all, we need to deal with effectively step 1. Step 1, what have I got to do? Well, during this phase, chip enable is low. So I'm going to make chip enable low. So I can't reach up there anymore. I'm not a giraffe, so I'm just bringing it down a minute. Let's bring it to there. Can you see more or less what's going on? Yeah. Right, so it's step 1. Chip enable's low, and chip enable's connected to P12. So I would say, I want to make P12 low. Well, I can do that by simply clear P12. If you want to be very nice, you could then sort of say set CE low. if you want to, but it's kind of good if you put some comments in, but I'm not very good at it myself. I should do it. It probably doesn't matter what's happening to the address bus here. This is going to be for the first value, I would imagine, in this region. So this could just be some initial value in here. So I would be tempted not to bother worrying about that. Now, how do I know it's not a particular interesting value there? Because in terms of the other signals, like chip enable and write, nothing exciting is happening around here. So I know that that particular value on the address bus probably really isn't an issue. So I'm not going to bother writing away there. It's whatever it is randomly at this point in time in this step. Write enable has got to be high, so I'll definitely deal with that one. Now, the write signal is P13, so I'm going to make that high. So set B, P13, set write high. Now looking at this, and it's not, I'm going to push this down a minute. The way this is written, if I was to sort of estimate when does data actually matter, the way this is drawn, I would say it's in this chunk here. What we're showing is some kind of initial value here, but in here, whatever the maker of this data sheet has done, they've shown a particular transition here and here and stable within that range. So by observation, I would expect that this, and this is actually taken from a data sheet by the way, I would expect this to be the place where the value on the data actually matters. So here, it probably doesn't matter yet. So during this phase, I would think it doesn't really, I don't need to say anything special about what's happening to data. And by observation, I'd also estimate that it's the rising edge of the write enable signal that's actually when the significant action is taking place. If it was this value that mattered, why would I bother putting a transition in here, if you see what I mean? So they've deliberately shown that there's some kind of transition here, then a stable period, and then there's some other kind of transition thereafter. So by observation, this is where I expect data to be the value that really matters. So for now, I'm not going to bother updating this, because we're back in step one, remember? So that's all the things that I would need to do in step one, is to set up basically the control signals, chip enable and write. In step two, we're then looking at what's going on here. Now there's a number of things happening in step two. During step two, the address is actually assuming, it looks like to me, a proper value. In fact, that's stable throughout the whole of these other bits. So we do need to set up the address bus with the correct value in step two. We've also got to do this thing with the chip enable. Now there's no phase relationship between those. They're actually shown as happening at the same time. So it probably doesn't matter which way around I do those, but I'm going to do them together. So, didn't need to bring that all the way down, did I? So step two, I've got to make chip enable go high. Well, that's not difficult. So set B, P12, raise CE. But I've got to do something else in step two. I've now got to put out the valid value on the address bus. To know what the valid value is, I've got to read what I've been told up here, and it says I've got to write in sequence, first of all, the value on the data bus 12 to register 1, 1. So the address value is 1, 1. Okay? And this is the address bus. Now I could do this individually a bit at a time, or I could write, well, I can't think of a better way of doing it, so we'll do it a bit at a time. So, now we want both of these to be high, so it's going to be a set B for these two things. So it'd be set B, P10, whoops, set B, P11. Setup, address, bus to 11 binary. Because why 11? Because that's what I'm told to do up here. I've got to write the value 12 to register 11 binary. Right, well, looking at this then, let's move this up a minute. Anything else happening during that step? No, no other transitions going on. Next one, it's just the right signal going low. So, step 3, clear whatever the right signal is P13. Nothing else happens in step 3. Step 4 is where I'm actually setting up the data bus. Okay? And there's nothing else happening during that phase, so step 4, I've now got to write onto the data bus the value 12 hex. Now, I could, for example, do this, which is what they're kind of implying. So I might do is move to the accumulator immediately 12 hex. Now, there may be an instruction to write immediately to a port. I don't know if there is or there isn't. You'd be able to check that from the appendix at the end of an exam sheet if there was a question like this. Let's assume that that isn't the case. I would do the move into, now I'm going to port 3, the contents of the accumulator. Now, strictly speaking, we're not using the whole of that port to write whatever value we've been asked to write, because not all of that port is in use. We're using 3.0 to 3.6, we're not using pin 3.7. But the way this is described, it doesn't say that pin 3.7 is being used for anything else. So we can probably get away with doing that. But be aware that we're actually setting pin 3.7 low in this case. So that may or may not be a problem. But in our case, we'll just assume it's okay. It's safe to do so. If that was potentially a problem for you, you only have 2 choices of how to do this. You set or clear the individual bits, which is tedious, or you read what's on the port, for example, into the accumulator, manipulate the bits that you wish to change, and then write it back. Anyway, so this is write 12 hex onto data bus. That would finish step 4, which is here. Step 5 is we then need to raise the write enable signal. So step 5, set B, whatever the write signal is, P13, raise write enable. Nothing else happens in step 5, and then step 6, we can start with changing, there's a whole thing, a set of things happening here. We're setting chip enable low, we're starting to prepare the address bus for the next cycle. This will all have been raised, and we're setting up the data ready for the next cycle. So, step 6, I need to lower chip enable, so that would be clear P12. Whoops, that's not P12. P12, set CE low. And then we could write on the address bus. Now this time we're going to write the value, I think it's 0, 1 binary. We'll assume the 1 is the least significant bit and the 0 is the next one. So the least significant bit of the address bus is going to be high. So that actually already is high, but we could write it anyway. Or you could just leave it as it is. I'll write it in. So that would be set B, P10, clear, P11. Both of those is to set up an address bus. Set up address 2, 0, 1 binary. I'm squeezing it in here, I'm afraid. That's the address bus, and then we would need to load up the next value on the data bus, which I'm not going to squeeze in there, but it would be something like this. At the bottom, it would be move into the accumulator immediately, whatever the value is, 0A hex. Move into P3, the contents of the accumulator. At that point in time, you'll have updated this. There's no change on this, and that's the last transition as shown on the timing diagram. What you would then do is effectively, this point corresponds to effectively, we're coming back into here again, but this time the address bus is set up, so you would then do another cycle of the write enable. Having done it for one cycle, given that the second cycle is effectively a repeat of the first, just with slightly different values, there's no need for you to bother to go into the details of what has to be done in the second cycle, because there's no significant difference between the first cycle and the second one. There are other ways of expressing this. This is just one example of code, but what matters is the sequence. Now, I'm not sure it's such a... There is an example that's provided here. I'll move this down a bit, but I won't rub it out just yet. For those of you, does anyone still want to see this? Anyone like a giraffe? I just want to talk to this one a minute. Here's another example. There may be slight differences to it, but the general sequence ought to be the same. Okay, so but you can look at that one at your leisure and digest it. So that kind of thing is useful, like I say, if you're doing anything in your design and build and you're using a data sheet, and it does happen occasionally, the student might come to me and say, well, I connected this to that, but it just doesn't seem to do anything. The first thing I always ask the student under those conditions is, well, show me the data sheet, show me the timing diagram, show me your code. And what I can do is compare the code with what the timing diagram sequence says should happen. Remember, it doesn't just give me the sequence, but associated with those timing diagrams in the real data sheet, you would also get information about setup and hold times. So we can see how quickly you're allowed to move between those steps. If you need to wait between steps, and sometimes you do, it might say you have to wait for 400 nanoseconds. What we would normally do there is insert a little delay loop in our assembly language to just do for however long, and then move on. Okay. And there are devices out there, quite a lot of them that we use, where, for example, the maximum speed at which they can operate is about 2 megahertz. But the microprocessors that we're using may well go beyond 20 megahertz. So they may well, if you let them, even if you get the sequence right, if it tries to do these transitions too quickly, it might be too fast for the peripheral that you're talking to. Okay, enough nagging about that, let's move on. Second part of the timing topic is really looking at, well, it's not to do with timing, it's about buses. So without buses, here I've got various, if you like, peripherals, electronic devices. One of these might be a processor, one of them might be some memory and things like that. And in this particular example, we're showing an arrangement of where these devices are connected through point-to-point wiring. And all the diagram is basically saying is, yes, you can build systems like this, but there is an alternative. And the alternative is to build them like this. The key difference between the two is where each of these particular devices have dedicated signal pathways. In this example over here, there is a shared signal pathway between the various entities. A shared collection of parallel wires we usually refer to as a bus. It doesn't actually say the word shared there, but a practical bus, the whole point of it is we're allowing multiple devices to have access to it. You can't let them have access to it, write to it, at the same time. In this arrangement here, although there's this bus that, for example, would allow C to talk to B or C to talk to A or whatever, that's fine. But it's no good if D wants to talk to B and C wants to talk to A at the same time. There'll be a conflict on the bus. We avoid conflicts on the bus by arbitration. Or if you want to say there's like a bus protocol to ensure who has access to the bus at a particular point in time. So, you've seen this kind of thing before. Generally we talk about there being address buses, data buses and control buses. The control bus is usually just a collection of special signal wires, like the write signal and the read signal, that kind of thing. The number of parallel wires that make up that bus we sometimes refer to as the width of the bus. So a bus that's 8 bits wide, i.e. the width is 8 bits, effectively comprises 8 parallel wires, allows you to transfer signals with up to 256 different values. Nothing exciting there. So buses are used as a shared communication infrastructure, but access to the bus must be controlled, particularly to prevent two things trying to write to the bus at the same time. Buses could be unidirectional, i.e. the data always flows in a certain direction on the bus, or they could be bidirectional. And we'll see how you can make a bidirectional bus. If multiple entities potentially can transmit on the bus, we need to use tri-state logic. And I'll explain how we make tri-state logic and how we use it to avoid bus conflicts.